Hi, welcome to this video on compliance voltage. I'm actually looking for some feedback on this video, so if you have further questions about compliance voltage, please do let me know about it. Now, when I say compliance voltage, I'm specifically talking about compliance voltage really with the use of low power potentiostats. So this is a Sensi All potentiostat from Zimmer Peacock. It works very well with our screen printed electrodes, and this kind of potentiostat is really intended to help people, both in their research, in education, but most importantly as well to actually get products to market. We think that a lot of technologies get stuck at TRL3. That said, this potentiostat is part of a movement where potentiostats are getting smaller and lower power. And this is where compliance voltage is becoming kind of this problem. And when I say problem, let me discuss it today. So what is compliance voltage, first of all? Why is there more discussion on compliance voltage these days? And what has ZP done to fix it? So these are the things that I will be covering today. As I say, I'm looking for some feedback on this video. So leave the comments underneath below, because I think I want to do a version 2 of this. So first of all, compliance voltage. So if we look at a potentiostat, and I'm biased, you know that I'm using the Sensi All potentiostat from ZP. But this is a good example of these kind of lower power potentiostats that are now coming on the market and are causing, I think, an uptick in questions regarding compliance voltage. So potentiostat, as many of you will know, the one parameter that people do understand is that a potentiostat allows you to apply a potential to the working electrode relative to the reference electrode. But what people don't know, and it's becoming more apparent to people now as this becomes a problem, is that the potentiostat's actually applying a compliance voltage between the working and counter to make sure there's enough current flowing between the working and counter to support the potential that's being applied at the working electrode. So the working electrode is being held at a potential versus the reference electrode. Great. But in order for that to happen, there's a second potential called the compliance potential that gets applied, or the compliance voltage maybe, that gets applied between the working and counter electrode to ensure that there's a current in order to support the potential between the working and reference. So in my diagram, you apply the, let's say the red arrow here, but you tell the experiment through the potentiostat what potential you want. The potentiostat tries to apply it, but in order to do that, it's actually then using a compliance voltage to make sure that the working and counter are doing what they need to do in order to support that potential. With that said, I'm going to, strictly speaking, I'm going to be talking today about screen printed electrodes, because I think screen printed electrodes like this, which are then often used in conjunction with low power potentiostats like this, that's now causing this uptick in people asking about compliance voltage. Once upon a time, potentiostats used to be quite big, and when they were quite big, they were mains powered. So you know the mains, depending where you are in the world, could be providing 240 volts, 220 volts, 120 volts, depending on where you are in the world. But quite a lot of power relative to the size of the electroanalytical experiment that was being performed. So let me just skip through a few things here. So I'm not talking generically about compliance voltage. I'm going to talk about it very strictly in the using screen printed electrodes as the thing I'm really kind of focusing on then. So let me replace this generic image with a screen printed electrode, which I'll do. And if you look at a screen printed electrode, it's really an electrochemical cell. You have a working electrode, you have a reference electrode, and you have a counter electrode. And when you put a solution onto these, you've then formed essentially your electrochemical cell. Now here I have a kind of a simulation of a cyclovoltammogram of ferrocyanide being run in on something like a screen printed electrode. With that said, if I look at this peak potential here, at that point, that working electrode is at about a potential versus a reference electrode of about 25 millivolts. But in order for that to happen, there's a compliance voltage being applied to ensure that there's a current of about 14 microamps. So the compliance voltage is applied to make sure that the working and counter are passing enough current to ensure that that 25 millivolts is actually 25 millivolts. Now, I think this picture on Wikipedia, so the reference here is Wikipedia, I think this slightly misleads screen printer designers because they think they will sort of follow this in some ways. And by following this image, you could end up designing a screen printed electrode that actually has quite a high compliance voltage. So let's talk about what is this compliance voltage doing. So let's imagine that we've got a resistor between our working and counter, and let's assume that we're passing something like 14 microamps between that. Now, if I was to run an instrument, if I was running this particular experiment, I might at this point find that my compliance voltage was 2 volts. What does that mean? That means that with a very simple resistor model, I've actually got a resistance between my working and counter of about 143 kilo ohms, which is very high. So the compliance voltage is actually to overcome this resistance and allow a current of something like 14 microamps to to flow. All I've used here is Ohm's law, so there's nothing super special about my maths. V is equal to IR, voltage is equal to current times resistance, and in order to have a current flowing of 14 microamps, I have to apply 2 volts, which means that the resistance between my working and counter was 143 kilo ohms. The reason I say that this image that's come from Wiki is slightly misleading because it would insinuate that was a good design for a screen printed electrode, but actually that design means that you would end up with quite a high compliance voltage, and then a lot of low power potentiostats can't actually deal with it. So let's talk about this a bit more. So as I say, this problem has come about really because potentiostats used to be quite large. I've got one up on the shelf now, but I can't actually grab it now. But they were quite large actually. I mean, I hold my hands like this, they're kind of this length, this high, and probably about this deep. I know that was just my hands, but they're quite big instruments. And when you've got a big instrument like that, you've got mains electricity going into it. You've got a lot of power going into that instrument. So when you're doing your little when you're doing your little electroanalytical experiment, let's say, it doesn't matter what your compliance voltage needs to be, because in some ways you're masked by the fact that the potentiostat has so much power. It does matter. There are all sorts of nuances to that, but you've got a big potentiostat with lots of power lots of power capability, so the compliance voltage can be sort of really ramped up by the potentiostat. The reason I say it does matter is because if that compliance voltage goes very high, you'll end up doing high electrolysis of water, for example. With that said, potentiostats now are becoming much lower power, so this is a kind of USB powered potentiostat that's maybe working through something like a smartphone. That's quite becoming common, and then they have a screen printed electrode put inside them, or slotted inside I should say. I don't like slots, by the way. Slots lead to ingression of liquid. When we were designing this, we made sure that there was actually no slot. In order to put this into here, it just clips closed like that. It's really kind of neat, and there's no possibility of ingression of liquid. So be careful with putting liquids on these kind of slotted in screen printed electrodes. With that said, these USB type potentiostats, and this is USB driven as well, so we're part of this, and this is why I can kind of comment on this, and also why we've come up with solutions for this. They're low power. You don't have infinite power, therefore you can't have essentially an infinite compliance voltage, so you have to be a bit smarter in the design of your screen printed electrodes. So at ZP we've actually, and this, first of all, a lot of screen printed electrodes sort of look like this, but there's some real nuances about this ZP501 screen printed electrode. Most people get this right in screen printed electrodes. They get the distances right. When I say the distances are right, the distance between the working and counter here is just a kind of a millimeter or just about a millimeter. So resistance is proportional to distance, so those electrodes are close, so the resistances are lower due to that distance. Area. This is something that people really get wrong. The reason I didn't like that wiki image is because the working electrode there is quite big relative to a counter electrode on the side. The reason that when I was doing my PhD, people said, oh, make the counter electrode 10 times the working electrode area. And people used to be able to do that when they had these large electroanalytical cells. Now, if you look at a lot of screen printed electrodes on the market, the counter electrode is definitely not 10 times the size of the working electrode area. First of all, you doesn't have to be 10 times the size. That was just a kind of, a rule of thumb. It was easy to remember, let's say. Why do people say that? The reason they say that is because if you have a large counter electrode, then you've effectively got a smaller resistance on that counter electrode. Resistance is inversely proportional to area. So if you make distances smaller, you make resistances smaller. If you make resistances smaller, you decrease the compliance voltage. If you make electrodes bigger, their resistance decreases, and their resistance decreases, the compliance voltage decreases. I just want to say something really careful. Actually, when I say area, I'm talking about the area of the counter electrode here. By the way, if you want to make the compliance voltage easier to handle, making the working electrode smaller, because when you decrease the working electrode, you end up decreasing often the current, and therefore the compliance voltage goes down. So maybe what's more important than just area is actually ratio, and I'm just going to cover this up for a second. Ratio of working to counter electrode. When you look at this ZP501 carbon electrode, that working electrode is actually quite small relative to that counter electrode. So maybe the ratio is a better way of thinking of it. I like what's good about this electrode is the distances are good. The size of this working electrode is big enough to, you can pipette onto it quite readily, but it's not so large that it produces quite a high current, because a high current will then drive a need for a high compliance voltage, and then the ratio between the working and counter is good. You can just see by eye that the counter electrode is sometimes bigger or not is bigger than the working electrode. Often now in designs you actually see that that's not the case. Now I'm going to show you a design actually where it's not the case. So I'm going to talk about materials. Sometimes Zimmer & Peacock is in a situation where my counter electrode here is just about the same size as my working electrode. So I've just broken my own rule about ratio, but actually we've made the counter from a material that has a very facile or very easy electrochemical redox reaction. So this is the bit that nobody talks about. People will talk about area and ratio, area of working electrode, area of counter electrode, ratio of those two areas. They never talk about the material construction, or it's very often not talked about. But here, by using a good choice of material, we actually made that that counter electrode much smaller. So you will see that we do have a design where it's smaller, but there we chose the right material. Now, people say to us, what is your compliance voltage? So Zimmer & Peacock, I'm thinking about using your screen printed electrode, and I hope you all would consider using our screen printed electrode. They're really well supported in terms of we really understand the science, the characterizations or the characteristics of these electrodes. But they also say, what's your compliance voltage? And actually, the compliance voltage, so for example, if you're using the sensor or potentiostat, now we've really tuned these kind of screen printed electrodes to work really well with our potentiostat. So compliance voltages for us has never been a problem, only because we really understand, we can predict the outcome of design considerations and then make sure that actually they don't get themselves into the product. But when they ask the question, what is your Zimmer & Peacock's compliance voltage? The question back is, what's the solution that you're trying to test? It's a really important point, see, because if you were doing the cyclovoltammetry of ferrocyanide, let's say it was 5 millimolar ferrocyanide, you would have a compliance voltage. If you had a solution of 5 millimolar ferrocyanide and 5 millimolar ferricyanide, your compliance voltage would dramatically decrease. Now, why is that? Because you've just added in your solution a molecule called ferricyanide. So when you're oxidizing ferrocyanide on your working electrode, your counter electrode can reduce the ferricyanide to ferrocyanide. You put a redox molecule in there, able to have a good interaction with the counter electrode, and you've effectively decreased the resistance of the counter electrode, in particular something called the charge transfer resistance. You just decreased it by putting in a molecule that interacts well with that electrode, and in my particular case it was able to receive electrons. The ferricyanide would become ferrocyanide. So it's really important that that question, what is your compliance voltage, can actually also depend on your choices, the user of these screen printed electrodes. Just something here, current. So I did, this is a little bit linked to my comment earlier on about electrode area. So that working electrode, often current is proportional to that area. So by keeping that electrode big enough to handle, but not so big that it generates a lot of current, then that does help with compliance voltage. As I say, this was never a problem until, and we do have, a USB driven, or not driven, but USB powered potentiostat. So this is an example of that kind of potentiostat where these things are lower power. And that lower, as I say, none of this was a problem with compliance voltage, at least in the world of electroanalytical chemistry, until potentiostats became much more like the Sensi or potentiostat. But as you can see, we've really thought through the screen printed electrodes. So in summary, was never a problem, but the potentiostats got smaller. The compliance voltage itself is this voltage that the potentiostat is applying to make sure that all the parameters that you're trying to control on that working electrode can be met, because the potentiostat is being clever and actually applying this voltage between the working and counter. And it was never discussed because, well, it was very rarely discussed because potentiostats were very powerful compared to, let's say, this experiment. But these days now, we're running off 5 volts or 3 volts, and as things become low power, this will become more of a problem. So as I say, it's just become a problem since these kind of USB driven potentiostats come along. But at ZP, I hope you can see that we've really thought through the problem, at least kind of the problem of compliance voltage when thinking about screen printed electrodes. As I say, I'm looking for some feedback on this video because I think I can do better. So let me have your comments underneath below. Okay, thanks very much.